Hope you have your sheets, because I want to go through those. Okay, so like I said before, we're going to so look at page 11 on those sheets. Talks about magnetic field and a current loop. All right. So last day I was talking about how we create a strong magnet using coiled wires, and all this was done by found out by a guy named Orsted, and then Amper jumped onto it. So a solenoid is a linear coil of conducting loops which takes the form of a helix. The core is the cylindrical column of air inside the loops or some material. Magnetic field about a solenoid. So I'll just show you this. Okay, so this is an air coiled solenoid. Okay. So what it is it just wrapped wire around it. So we hook up the ends of it to your anode and your cathode, and we provide an electric current through it. And as you provide an electric current through it, you create a massive magnetic field inside of here. All right. So the other day I was trying to explain a super magnet to you. Basically what that is if I stuck an actual magnet inside here, okay, and then wrapped it around, and let's say I had the ends pointed out, the poles pointed out, I would create a massively stronger magnetic field around that magnet itself. Okay, so those are the types of, so that's what they do with the super magnets for when they're lifting cars with in an area where they move the old cars and they put them into compactors and everything like that, the old metal and stuff. So that's what they do, is they wrap the magnet around with wires. They send a current through the wire and around the magnet, and it creates a massive magnetic field. And the reason it creates a massive magnetic field is because the electrons are moving, and they're moving in two directions. They're moving in the direction of the current. So that's what the diagram shows. They're moving around the coil that way, plus they're spinning. And when they spin and they move in the same direction, they create a much stronger magnetic field around it. So Amper's rule for a solenoid is grasp it in the left hand with the fingers circling in the direction of the electron current, and the extended thumb will point in the direction of the north pole of the core. So depending on how that happens, salvage yard is the word I was looking for anyways. So if I set my left hand like this, this is, if the current is flowing around in this direction, following my fingers, then that means that this is the north end pole here. Okay, so that's that. I put my fingers on here in the direction of the current. Okay, so if the current was flowing in the other direction, this would be the north end of the pole here, rather than this end, because this is the way the direction of the current is. So there's two rules, and the rules are set there. The only reason that you want to be made quite aware of them is it changes the equations for you. So when we try and find out the magnitude of that force, okay, the magnitude of that force is different between a straight conductor and a solenoid. So if you look at the equation sheet that I provided for you, it says the B, so the B is your magnetic flux density, okay, the strength of that magnetic field, all right? If it's a straight conductor, you use 2 pi k n, which is the number of turns. I is the current, and the R is the radius of the actual conductor itself. So that's like for a straight wire. That would be like if this marker that I'm holding right here is a wire. That's how it would work, okay, for a straight conductor. If you're talking about a solenoid now, you're talking about the area. So you've got the 4 pi k I n. So it's the same idea, except it's 4 now. And then you're talking about the length of the wire. Okay. So 19.11 talks about the strength of an electromagnet. So for a given core material, the strength of the electromagnet depends on the magnitude of the current. So the stronger current you have, the stronger the magnet you have. The second thing that affects it is the number of turns. So the number of turns that the wire goes around, the number of times the wire goes around, that determines the strength of the electric current. The strength is determined by the number of ampere turns. Look at page 13 now. This is where we're going to get into some of the word problems that we're going to use. Okay, so a tiny section of wire carrying a current is placed within a magnetic field. The conductor is pointed in different directions and the force is measured. So if the deflecting force is perpendicular to the direction of the current, you're going to have a maximum force. That's shown in B. In the first one, the current is running parallel to it, parallel to the lines. The force is 0. So to get the maximum force, it's in direction at a right angle to the 0 force direction. So if you stick it into the magnetic field, parallel to the magnetic field, you'll have 0 force. But if you stick the wire in at perpendicular, you'll have a much larger force. The force is directly proportional to the length of the wire and to the amount of the current. So to get your maximum force. So again, what we're talking about here is I have a magnetic field and I'm sticking a wire into it. All right. So on one of those videos that I sent you, I'm pretty sure it's on there. Anyways, if you took a horseshoe magnet, okay, so I have a horseshoe magnet. So the strength of my electric field is in here. All right. There's still some magnetism on the outside, of course. But the strength of the magnetic field, if you had iron filings, the majority of them would be on the inside of there. So if I were to drop a wire in perpendicular, so drop it in here, okay, it would actually kick it out of there. All right. As soon as you turn the current on, it would push the wire out of that magnetic field. So what we want to do is we want to calculate what that maximum force is. We want to calculate what that maximum force is inside that magnetic field when I put a wire in there. To do that, I need the amount of flux density, okay? And that's measured in newtons per amp meter. Okay, so I'll write that down here. So that's newtons per amp meter, okay? The amount of current and the length. And the length this time, so when we worked with resistance, we did the length as centimeters. Now we're going to do the length as meters, okay? And if this is newtons per amp meter, you'll notice that this is in amps and this is in meters. They cancel, and it leaves us with the force of measured in newtons, okay? So let's look at a question. And again, I'm on the worksheets or the abbreviated material I sent you, okay? A portion of a power line carrying a direct current of 100 amps is 100 meters long. So I've got a current 100 amps over a length of wire 100 meters long. The wire is at right angles to the Earth's magnetic field, whose magnetic induction, so that's my B value. Call it magnetic flux or magnetic induction. It gives it to me as 5 times 10 to the negative 5 amps per meter. It says, what is the magnetic deflecting force in this section of the power line? So F equals BIL, 5 times 10 to the negative 5 times 100 times 100. I get a magnetic force of 0.5 newtons. Okay? All right, so that's not very complicated. All right, now, current, when we talk about current, current is coulombs per second. So it's the amount of charge that goes through a given point in a given amount of time. So that's Q over T, in which I have the amount of charge over the amount of time. Okay? So what they want to do is, it says, consider what happens to the electrons in a straight wire of length L with a current I at right angles to a magnetic field of induction B as they drift down the wire with a velocity of V. So now they're going to introduce a velocity. The wire contains n electrons moving in the current at any instant. Each electron carries a charge E, so that the total charge is NE. So what they're saying is this. Okay, now charge, remember, is 6.2, 1 coulomb of charge is 6.25 times 10 to the 18 electrons. So if I take the number of electrons and I times it by the charge of an electron, I come up with the number of coulombs. So I have NE over T. At some time T, all of the electrons will pass over the cross-sectional area. So when it's all said and done, if I do some substituting in for I, what I'm going to come up with is F equals BEV. All right? And B is my induction still, doesn't change. E is my charge on the electron. All right, that value doesn't change. And my V is the velocity at which the electrons are moving. Okay, in meters per second. All right. So all they're doing is they're just creating a little bit more work here. An electron with a velocity of 5 times 10 to the 6 meters per second. Initially, it goes from south to north, enters an east to west magnetic field, where B is a constant. It says, what is the deflecting force acting on the electron? Okay, so the charge on an electron is 1.6 times 10 to the negative 19. It's talking about one electron. So now I just need to put it into my equation. F equals BeV. So the amount of force on that electron is 4.8 times 10 to the negative 15 newtons. Okay, so it says, what is the deflecting force acting on the electron? The second thing says, what is the radius of the circular path of the electron if its energy does not change? Okay, so this is brand new to you as well. we use this for centripetal force. Okay, so we want to find out what the force is moving in a circle, given our mass, our velocity squared, and our r. So we're looking for the radius. So the radius is the mass. So the mass of an electron is also given to you, and it is 9.1 times 10 to the negative 31 kg. So we can look that up. We have our velocity, 5 times 10 to the 6, that's squared. And we're going to use our force to calculate our radius. And our radius works out to 4.7 times 10 to the negative 3 meters. Okay. Trying to get these all straightened out. All right. So, what I would like you to do is, there's a worksheet at the back of that. And it starts in worksheet number 5. Is I would like you to do for tomorrow questions 3 and 4 on those worksheets. So you're going to spend most of the time working with your new equation sheet. All right, but there still is a little bit of work to do. Just that force equals mv squared over r. It's not on that sheet. Okay, but you may need it. All right, so question 3 and 4 on that worksheet 5. If you can attempt that for tomorrow, I'll go through those with you tomorrow, and I'll go through most of that sheet with you tomorrow and Friday. All right. So we're going to wrap this up. Actually, I don't know, maybe mine's not in order. What's the first worksheet you have on that package?
I'm not sure because I have on my thing to get my phone to get it. Could you take those sheets home today by tomorrow?
Can I take them home?
Yeah.
Yeah.
And I can come pick them up at a hard call.
Okay. Yeah, no problem. Okay, so actually what I want you to do is there's 3. There's a worksheet number 2. That's the sheet that we're going to do. We'll do questions 1 to 3 on worksheet number 2. So it has a number 2 at the top, and we'll do questions 1 to 3. So that's on the earlier stuff.
Okay.
Okay. So we'll do that for tomorrow, and then I'll go through those with you. I'll go through 4, 5, and 6 with you tomorrow, online. Okay.
All right.
Daylin, I see you on here. Any questions today from math or physics?
No.
Okay.